one of the things I love about the enabling technologies track is everything that you see here is not academic, oh, this will be something in 5 years. The enabling technologies track is about real products. It's about building stuff that actually works. And the thing that amazes me about it is just how astonishing the products are in this track. So when I'm not being a track moderator here, I'm one of the people who reviews slides. And when I first read this title, Machine Learning Inference in under 5 milliwatts with a binarized neural network, BNN, and an FPGA, I'm like, oh yeah, it's a typo, right? Because nobody does DNNs of any sort in 5 milliwatts. And I was wrong, because it turns out not only do people do that, but you can buy a chip today that does it. So our first speaker is Abdullah Raouf from Lattice Semiconductor. He's a senior marketing manager, and this is awesome, and you're going to be amazed by it. At least I was. Abdullah?
All right, hello everybody. My name is Abdullah Raouf, as Phil mentioned, and yes, it is true. This is a solution that's on the market and available today, and we can do deep neural networks in under 5 milliwatts. I'm not sure if everybody here is familiar with FPGAs. They are programmable hardware that you can program to do virtually many different applications. What we're offering today, what we're announcing, is the ability to put deep neural networks inside of these FPGAs. So before I get started, let me talk to you kind of what the agenda is going to look like for today. First, I'm going to talk about this shift of going away from intelligence only in the cloud to intelligence on the edge. And I want to kind of define what edge is, because I've seen a lot of people define edge a little bit differently. Edge, in my presentation, is the products that are gathering the sensor data. So the products that have the sensors, the microphone sensors, the image sensors, and are collecting all of this data. And in the past, all of this data would be sent to the cloud for analytics and all of the intelligence in the cloud. I'll give you an example. If you want to find out what time it is with an Alexa, you say, Alexa, what time it is? And if you're not connected to the cloud, you get no response. Although Alexa should know what time it is locally. It has, sometimes there's displays and the clock is right there, but it's not able to tell you because it needs that cloud connectivity. We're trying to show you that you need to move some of that intelligence locally, and there's a couple of reasons why. So I'm going to talk about why is edge intelligence important. Then I'm going to introduce who is Lattice and what are we releasing to the market to enable vendors like yourself or solution developers to go off and quickly develop something in terms of artificial intelligence and do it in a power efficient manner. So that's kind of the flow of today's presentation. So why edge intelligence? So there's a couple of reasons. Number one, people want immediate response back. And that means they don't have time to wait for the cloud to process the data and give you the results. So there's an example here of a guy driving a car and there's a person in front of him. Do you want to wait seconds for the camera image to be sent to the cloud? The cloud tells you that there is a person in front of you, so the car needs to brake. You don't have that much time. You need to react instantly. So in order to react instantly, you need that analytics to be processed locally. And I'm just showing a car, but there's tons of examples out there. Small drones that are battery powered with small 3,000 milliamp hour batteries need to process this information quickly and locally. The second point that I'm making is a lot of this data is private. And people don't want their private information shared in the cloud all the time. They only want certain information being shared in the cloud, so what we're saying is process the information locally. You don't need to send anything to the cloud. Everything is stored inside of the local device, and it's processed there. And I have some quotes. So I come to a lot of these talks, and the number one thing I take away from these talks are the quotes, because I get to use them in my presentation. So I'm going to give you guys 2 free quotes. One is by IDC. By 2019, 45% of the IoT-created data, that's the data sitting at the edge being gathered by all this sensor data, is going to be stored, processed, and analyzed locally. Another quote, unit growth for the edge intelligence, the AI capability on the edge is going to increase 110% CAGR over the next 5 years. So this is not just something that we see. This is what the industry sees. Edge intelligence is happening. All right, so now let me introduce who is Lattice. Lattice is an FPGA vendor. We offer the world's smallest FPGA. We have FPGAs as small as 1.6 millimeter by 1.6 millimeter. Now that's small. Now for artificial intelligence capability, we're offering a slightly larger FPGA, 2.1 by 2.5 millimeters. And that's a picture of the FPGA right there next to the salt grains. Inside of that chip, you can integrate a deep neural network. And that chip costs around $1. And that chip will support the deep neural network in 800 microwatts. So we're talking about 800 microwatts, a dollar solution in production now, and it's that small, and you can implement a deep neural network in your solution today. So how do we fit compared to all the other? You're going to see a lot of solutions out there during this conference. And this plot kind of shows how we match up against all the competitors. Let me explain the y and the x-axis first. The x-axis shows their performance. How many neural operations can you perform within a second? The y-axis shows your power. Now, the Lattice Sense AI, so I'm going to introduce Sense AI in the next slide. This is a platform that we're offering to our customers. And this Lattice Sense AI provides solutions within this yellow region. And this yellow region, as you can see, is everything below 1 watt. And it's everything to the left of 1,000 billion neural operations per second. Now, I have 2 chips here you can see. One is called the ECP5. I don't know if you can see that. That's one of our FPGA families. The other one is our ICE FPGA family. So just understand there's 2 FPGA families within Lattice. ICE is our lowest power. We call it ICE because it's very cool, very low power. That's what I'm going to focus on today, the ICE. So I'm going to focus on less than 10 billion neural operations per second and less than 1 milliwatt. Now, the title of the presentation said less than 5 milliwatts because that's the total solution. That's with the sensor data. That takes you up to 5 milliwatts. But the actual processing is under 1 milliwatt, 800 microwatts to be exact, which is what I showed on the previous slide. So that just kind of sets up where do we play. And there's a word here that I showed, AI coprocessor. Because a lot of times, a lot of systems need a lot more powerful processing. So you can classify us as a coprocessor, and I'll explain what that means. How we do part of the processing, wake up a more powerful processor that's going to consume hundreds of milliwatts, but we only wake it up in certain intervals. We don't wake it up all the time. So we're sitting there always on, always intelligent, consuming little power. The powerful processor wakes up once in a while and does the additional processing that's needed for a total solution. So you guys understand what Lattice is and kind of where we fit in. Now let's talk about the Sense AI stack, which was just released yesterday, by the way. So if you go to our website, you can get a lot more information, but I'm just going to give you a quick overview of what Sense AI is. So I'm going to set up the slide again. The x-axis is showing the power capability. So on the right side of the slide, we talk about that 1 watt, that ECP type FPGA. And on the left side, we talk about that 1 milliwatt, $1 ICE FPGA. I'm going to be focused on the left side. And I'm also going to explain what we're offering in this stack. So in this stack, we're offering a few things. We're offering hardware platforms that's going to allow developers to quickly pick up our FPGA and quickly start playing with it and start developing solutions. These development platforms are already in production, already available by many of the popular distributors worldwide. Above that, we offer our IP cores. Now, the IP cores are our BNN accelerator, which is focused on the left side of the screen. So BNN is a deep neural network using binarized weights. That means your weights or activations are either 0 or 1. The value of that is you're not storing 16 bits of weights and activations. So you're storing 16 times less, so you need 16 times less memory. Also, you don't need to use any multiplication when you do your computation. You're only doing addition or subtraction. That means your processing requirements are a lot less. That's why we chose binarized neural networks. Now, that doesn't mean we're limited to binarized neural networks on the left side of the FPGA. We can do 16-bit neural networks as well, but we chose to do binarized neural network, and that's what we're offering for free. So our IP cores are available on our website right now for free. We're not trying to make money on our IP. We're trying to make money on the FPGAs, which is what we're trying to sell. So you can go to our website right now, sign a license agreement, and you can download our IP cores and start playing with it right now. We also offer tools, software tools, that allow you to use the IP cores. And these software tools also allow you to connect to popular training platforms such as Caffe and TensorFlow. So I didn't kind of classify what inference meant. I assumed you guys understood it, but there's always 2 categories to develop a full AI solution. One solution is you have tons of data going to the cloud to do your learning, and that's to learn and create a model. We don't play in that part of it. Once the model is created in Caffe or TensorFlow or one of these popular platforms out there, that model is then put into our FPGA, and that's where the inference happens. We take new sensor data and we compare it to the model that was created, and we infer, was there a match or not? So the software tools take the model that's created in TensorFlow or Caffe, and it ports it or bridges it to our software tools that helps you develop on an FPGA. Those tools are available for free as well. Go to our website, sign the license agreement, and you can have access to that right away. And we also offer reference designs. We have reference designs. The first two reference designs are targeted towards that left FPGA. Around 3:30 today, there's going to be another talk that's going to focus on the right side, the 1-watt FPGA. So come listen to that speech as well. But I'm focusing on the left. So there's two reference designs that we're offering, again for free, are the face detection and the key phrase detection. So both of those, they have tons of data in the cloud. We use Caffe to do your training. We created a model. We put the model into the FPGA. And then we can do real-time inference in 10 milliseconds. In 10 milliseconds, we can compare new data to the model that was created. So we're offering this entire platform, this stack, hardware, IP cores as a reference, bridge tools that allow you to bridge from the popular training databases to our software development platforms, and we're giving you reference designs. Go to our website and you can learn more. So what I'm going to focus now on is the actual chip, that Ultra Plus, that ICE family FPGA, and I'm going to explain what it is and why we're offering this solution and how it's really going to help you guys. So these slides are going to be available to all of you. So I'm not going to go through all of these, but this is a great reference slide so you can refer back to it. Because this FPGA has a lot of intelligent blocks. Remember, this FPGA is that small 2.1 by 2.5 millimeter FPGA, although it has a lot of different key elements. It has the memory you need to store your neural net weights and activations. And guess what? That memory can be reprogrammed. So that means if your solution is deployed in the field, and you relearn to make your system more intelligent, and you got new weights and new activations, well, you can remotely update those weights and activations. That means your system can continually get more intelligent. We also have the hardened IOs, the flexible as well as hardened IOs, therefore we can connect to many different sensors out there. Image sensors, audio sensors, vibration sensors, gyros, accelerometer, you name the type of sensor, that is the main value of an FPGA, is the flexible IOs that can be programmed. So again, I'm not going to go through all these building blocks. This is a great reference slide. Now, I've kind of already verbally explained how the flow works, but now I'm going to show you in a more picture-esque element on how the flow works for a full AI system. So number one, you have tons of data. It's untrained. You want to use Caffe or TensorFlow to take all this data, and the example I'm going to be giving is human face detection. We have 500,000 images. We put these 500,000 images through TensorFlow or Caffe, and we create a model. This model goes through the SenseAI network compiler, and this model is restructured to fit Radiant, which is the Lattice tool that's needed to program the FPGA. Then this model is integrated into the ICE FPGA, and then we get new data that comes into the FPGA, so we compare it to that model. And whenever the result says there is a match, we provide that information back to the system. So for example, for the human face detection, anytime a new human face goes in front of the image sensor, we say that indeed is a human face. And we do this, like I said, in 10 milliseconds. That's all the computation time we need. And the way we provide the 800 microwatts, which I referred back to a few slides ago, is we basically turn on for 10 milliseconds, then we turn off, then we turn on, then we turn off, and we keep doing that so that we only turn on 5 times a second. And by doing that, we go to 800 microwatts. And this small little FPGA has a performance of 1.1 tops per watt. Try to find a smaller solution that can support 1.1 tops per watt. This is indeed the smallest solution out there. This next slide shows again another picture version of what I already said. Caffe TensorFlow gives you these output files. We offer the SenseAI network compiler that takes those output files, converts it to something the FPGA can understand. At the same time, you have your accelerator IP, which, by the way, is flexible. You can customize to meet your needs. You don't have to use our reference IP as is, although you have access to it, and you can. So you have the accelerator IPs coming into the same FPGA, along with the weights and neural the activations, and now you have a total solution. So this is what the entire flow is going to look like. Let me show a real-life example. This is the face detect. So this is what the neural network structure looks like for face detection. This is the neural network structure that we're offering as an IP for free as long as you sign a license agreement. And some things that I want you to take away from the slide are, number one, it's a 7-layer BNN that we're offering. It offers 2 classifications. Either the object is there or the object is not there. And the object in question here is a face, human face. The input to our neural network is in CMOS image sensor at 32 by 32 resolution. And if we support all of these 3 points, the amount of memory that we needed, because we're using binarized neural network, is shown in this table. What I want you to take away is if you go to the 1 bit in the activation, we only need 17 kilobytes. 1 bit in the memory, we only need 15 kilobytes. That's 32 kilobytes of memory needed. That's it. And that's your entire weights and activations. And I told you earlier we have 128 kilobytes in our FPGA, so that means you don't need any additional memory. This small FPGA by itself, no additional memory, can be your entire compute engine for inferencing. A single chip solution that's in production now. On the right side, I show us connected to an image sensor. The ICE FPGA consumes 800 microwatts. The image sensor also consumes some power. We found this Himax image sensor. I don't work for Himax, but I think it's a very low power image sensor, so I want to mention it. It only consumes 1.4 milliwatts. Together, your total solution is 2.2 milliwatts, well under that 5 milliwatt number that Phil thought was a mistake or a typo. It's well below 5 milliwatts, 2.2 to be exact. And by the way, there's a live demo of this demo at booth 502. Please stop by, come take a look at it, play around with it. Wear glasses, it'll detect your face. Wear a hat, it'll detect your face. Close your eyes, it'll detect a face. Look to the side, it'll detect a face. Wear a cap, it'll detect a face. Have a beard, it'll detect a face. Come check it out at booth 502. Now, I told you we're the AI coprocessor. So the coprocessor does the detection. You have your weights coming through SPI. Actually, let me set up the slide first. The FPGA has a bunch of resources, and what I want to show you is that we don't even use all of the resources available. So the table shows the available resources and what we actually need. So it's an FPGA. You can program and do whatever you want. So if you wanted to add more functionality, you still have LUTs, DSPs, and memory so that you can do more with it. However, if you want just AI and you just want our solution, the FPGA is enough for you to use. So I said we're a coprocessor to the main processor. We basically send the result to the main processor. We have it wake up, and it can do a secondary check. It can do more of a check. For example, it says, OK, there's a face there, but whose face is it? It can actually do that secondary check and say, OK, now this is this person. And in our booth, we actually have that demo. You walk up in front of it. It sees there's a face there. Another powerful processor wakes up and says, whose face is it? So that demo is also there. So what type of applications need this? Maybe a smart LCD screen on your refrigerator. You don't need it to always be on until a person is standing in front of the refrigerator. Maybe your TV. You don't need it to always be on unless someone is sitting in the living room on the couch ready to watch TV. And when you walk away, you want your TV to turn on. When you step up in front of somebody's door, you want the doorbell to ring on automatically. You don't want someone to have to press a button. And you don't want a dog or the sun movement to cause a doorbell. You don't want false doorbells. You only want a doorbell when there's a person present. So these are just some examples of when is somebody care if a general person is standing there. Not a specific person, just in general. Why would people care when somebody is standing there? And this is what the total solution looks like. Next to a finger, you can see all you need. Again, no memory. You need the image sensor circled in green. This image sensor is the OmniVision image sensor. We've actually done our training and our inferencing and our proof source on 2 image sensors, the Himax as well as OmniVision. But our IOs are flexible, our FPGA is flexible. You can program it to support different image sensors. And then you need the FPGA circled in blue. That's all you need. No memory, nothing. That's your entire solution. And the demo that you'll see at what booth? Booth 502. Is basically going to have this board in front of you, and whenever the LED light blinks or stays solid, that's when it sees a face. So come take a look at this demo at our booth. Now, I have a lot of data that's also in these slides that I'm not going to go through that talks about how much of an angle can you detect a face this way, and this way. Also, how much light can you detect? How bright can it be? How dark can it be? All of that data is very valuable, but it's not going to be presented here today. It's in the slide deck. You're going to get it. I think everybody's going to get these slides after the presentations are over. So in summary, 1-bit weights and activations to fit into the memory footprint of our FPGA. We can connect to external memory, but we don't want to. We want to keep the system costs low. So we want to get down to 1 bits weights and activations. Although we're not limited to 1 bits, we can do 16 bits, keep that in mind. But the reference designs and the free tools we're offering today are for 1 bit. We can consume 0.8 milliwatts at 5 frames per second and offer a single item object detection today. We're standalone, no memory, just our chip and the sensor data. That's all we need, and we can do inferencing at the edge. Our chip is only 2.1 by 2.5 millimeters in size, and we can get to 99% accuracy. So to learn more, stop by our booth at 502, visit our website, or contact myself. So we have about 5 minutes left. I think we're going to take some questions now.
Yep, we will take questions, and if you have questions, please come up and use the microphones here. And I have a question for you, Abdullah, while we're waiting for folks. So this is an awesome application. Are you guys working on kind of next generation IPs that you might also offer? And are you in a position where you can reveal what those might be? What's the next thing beyond detecting a human being or not as a face?
Great question. So yes, we are definitely evolving and trying to improve our capabilities. Right now we detect one object. It doesn't necessarily need to be a human being. That's just the training database that we have. So that object could be a car or not a car. But we want to get to more objects, not just one object. We want to get to voice comparisons as well. Multiple words, stop, play, volume up, volume down. We want to get to that as well. We want to get to other sensors. So for example, right now our demo uses a CMOS image sensor. CMOS image sensor gets the entire information from the person, what the person's wearing, everything about them. People don't want that information to be stored in a machine, even though they know the machine is not a person, it's just a machine. What if we went to PIR sensors? Right? You don't have any information about the person, but you can differentiate between a cat, dog, and a person. So those are the kind of steps we're trying to take in order to improve this capability.
Super interesting. Thank you. Any other questions? Can you come and use the speaker, or the microphone rather, please?
I did not show the false positive or accuracy rate, although I do have the results in the summary of results that talk about that. For example, if you were to go here, you can see the false negative rate and the false positive rate and how it changes based on the brightness of the image coming in. This data is available to you guys. I didn't want to go through these kind of details. The reason why is because this is heavily dependent on the training data. We are not a training database company. We are an inference company that we were hoping that you guys have your own training data, and that your training data is going to significantly change these performance metrics. This is just one example. But again, you have access to this.
Great, thank you. Yes?
I have a question here. So if we are a training company and we have trained our networks at 8-bit or 16-bit, and if we're implementing at Binarized, what kind of loss in accuracy have you seen?
We actually prefer that you do the training on 1 bit. We tried training on 16 bits and quantizing it down to 1 bit. And actually, there's a talk tomorrow at 10:50 that talks about deep quantization. And I think in that talk, we're going to talk about how we prefer the training to actually happen in 1 bit, or else you're going to lose too much performance.
Okay. More than performance accuracy.
Accuracy, that's
we'll
what
gain
I mean.
performance.
Correct, accuracy.
Do you have any numbers in terms of 8-bit tops per watt?
I do not have 8-bit tops per watt. I just have the 1 bit, which is 1.1 tops per watt. Yeah, I don't have that number off the top of my head.
And actually, a follow-up question to that is, do you provide with, I think you mentioned both Caffe and I think also TensorFlow, if I saw correctly.
Yes.
Do you provide kind of examples of doing that 1-bit training in that?
Yes, so we offer the 1-bit training on face
Okay.
and the 1-bit training on a key phrase. So yes, we do offer examples.
Awesome.
Yeah.
And it looks like we have another question.
Yeah. I'm curious, you offer support for TensorFlow, but there's a few more competing frameworks like PyTorch and MXNet, to just mention a few. What's your view on those? Do you plan to support them, or why did you pick TensorFlow first?
We feel it's the most popular. We feel it's open source, so it's very easy to integrate our solution into it. There's a lot of other solutions, and there's a lot more coming. It's going to be very difficult, nearly impossible for us to keep up with all the tools out there. Right now, our plan of record is to support these 2 open source tool sets. In the future, if we see a lot more interest in the other tool sets, we may adopt them as well.
Have you looked into those exchange formats that are around, ONNX and NNEF and similar, as an option to support more frameworks?
So we have looked at supporting more frameworks. Again, it's all about how much more popularity is going to be in them.
Yeah, I just mean this is an exchange format, so you only need to support that format. And then you can rely on other the companies providing their own exporters to the format.
Yeah, that's a great idea. Yes, we could definitely look into that. At this point, we haven't, but that's definitely a possibility. Great input.
Okay,
Thank
thanks.
you for that. That's a very good.
In your human detection demo and circuit, is the ISP for the sensor also implemented on the FPGA?
Yes, so we have to actually downscale the image. The image sensor we're using is a VGA resolution. We need to downscale it, have some ISP functionality built into the FPGA, which is a soft core as well. We offer that IP as well.
Okay.
Yeah, good question.
Awesome. All right, Abdullah, thank you very much. Fascinating.
Thanks, everybody.